Hello everyone. We will be presenting our project titled Pneumonia Detection using ResNet50. The goal of this project is to explore how deep learning can assist in identifying pneumonia from chest X-ray images. Coming to introduction, pneumonia is a serious lung infection and a major global health concern, especially for children, elderly, and people with weak immune systems. Early detection is crucial to prevent severe complications. While chest X-rays are widely used for diagnosis, interpreting them and can be challenging due to subtle abnormalities and variations in image quality. Diagnostic challenges are diagnosis today relies heavily on radiologists manually examining chest X-rays. This creates several challenges like interpretation can be subjective and prone to variability, and radiologists face high workloads, especially in emergency departments or rural clinics with limited staff. Inconsistencies may occur due to human fatigue or lack of experience. Now, a deep learning for chest X-ray analysis, particularly CNNs, have shown tremendous success in image recognition tasks. These models excel at identifying patterns that humans may overlook. Residual networks like ResNet50 are especially powerful because their skip connections allow networks to learn deeper feature representation without vanishing gradients. Medical images such as chest X-rays have subtle abnormalities, making these high-capacity models ideal for the task. Coming to the project objective of our project is to develop an automated pneumonia detection system powered by ResNet50. Our goals include designing a pipeline that can process chest X-rays from input to classification, leveraging transfer learning to adapt ResNet50 originally trained on ImageNet to the medical imaging domain, achieving high accuracy, incorporating interpretability methods so that clinicians can understand why the model reached a certain conclusion. Ultimately, our aim is to assist radiologists, not replace them, by providing an additional diagnostic tool. Now, let's come to the dataset overview. We use the Kaggle chest X-ray images, that is pneumonia dataset, where it contains around 5,863 labeled images. The dataset has two classes, normal and pneumonia, and is split into training, validation, and test sets. One thing to note is that pneumonia images significantly outnumber normal ones, so we incorporate class weights during training to balance the model training. We also applied pre-processing steps like resizing and augmentation to improve generalization. Now let's see the workflow. Uh, First, this slide shows the full workflow of our system from input to output. First, it takes the raw chest X-ray image that is fed into the system, and next, coming to the pre-processing step, we resize the images to consistent resolution, normalize pixel values, and apply augmentation during training. And next is the ResNet50 model. The pre-processed image passes through our fine-tuned model, which extracts deep visual features. And next step is classification, where it interprets the features and outputs a label. Next comes the prediction output. The model produces a probability score indicating whether pneumonia is present or no. And next is ResNet50 model. Our architecture builds on top of pre-trained model. First, ResNet50 acts as a feature extractor. We remove its original ImageNet classification layer so we can repurpose the model. Then we add a new classification head customized for binary classification. ResNet50's deep layers help capture subtle abnormalities in lung texture and opacity, features that are highly relevant for pneumonia detection. And the classification head details are Global average pooling, which compresses spatial features from convolution maps into vector form. A dense layer with 512 units for high level learning. A 40% dropout layer to prevent overfitting. And finally, a sigmoid neuron that outputs a probability between 0 and 1. Now, here is my teammate to continue.
Coming to two-stage transfer learning, our models use two stages of transfer learning process to get the best performance from the ResNet50. There are two phases. First phase is we freeze all the predictive ResNet50 layers and train only new classification head. A significant higher learning rate is used to because only a small part of a model is been updated. This helps the new layer quickly learn the pattern in the chest X-ray without disturbing the useful features already learned from the ImageNet. Coming to the phase 2, next we unfreeze the layers of 40 layers of ResNet50 and fine-tune them using a smaller learning rate. This allows the deeper layer to slowly adapt the medical specific features like lung textures and opacity. These two stages processes gives us stability from the predictive knowledge and flexibility to specify the model, leading better accuracy. Coming to the key optimizations, to make the training more efficient, we use added several optimization methods. Some of them are class fit, helps to balance to data set so that the model doesn't favor the predictive classes. Coming to the model checkpoints, automatically saves the best performing model during the training. Coming to reduce LO or lower learning rates when the process slowly helping the model refine its learning. Coming to early stopping training when the validation loss stops improving the predictive overfitting. Coming to fixed predictive training, it speed ups the training and reduce the GPU memory use. Coming to the next slide, it's a grad cam interruption, where the grad cam interruption is very important in the medical AI. It helps us to understand the model focusing on. For normal X-ray, grad cam typically highlights the clear lung regions, shows these models to verify the abnormal areas are present. In pneumonia X-rays, grad cam highlights the dense of the cloudy area that corresponds and of the infection. These are the same reason radiologists focus on, which increases trust in the model. Overall, a grad cam makes a model's decision and ensure it's learning meaningful medical features rather than the random artifacts. Coming to the result summary, our final model performs very well. 91% of accuracy, meaning it correctly classifies most of the test images. 0.96 ROC and AUS shows the excellent ability to distinguish between the normal and pneumonic cases. These results indicates our training strategies and optimization work efficiently, and the fine-tuned RES50 model able to learn strongly. Here our next team is going to.
To conclude, our project successfully demonstrated the potential of transfer learning based deep learning models for pneumonia detection. We have shown that ResNet50 can be repurposed for medical imaging and high accuracy and with useful visual interpretability. Now let's move on to the references part. The listed references provide the academic and technical foundation for our project. They include prior work such as ChestNet, ResNet theory, data set sources, and related diagnostic studies. These works support our methodology and validate our approach scientifically. Now that we have covered the technical foundation and results, I'll move on to the demonstrating how our system actually performs on real X-ray images. Now I'll be demonstrating the implementation of our pneumonia detection system using a fine-tuned ResNet model. I'll walk through the code execution, summarize what each part does, and finally run a live test on an actual test X-ray. In the first step, we install all the necessary dependencies and libraries such as TensorFlow, Keras, Kaggle Hub, and other required libraries. Next, we import all the modules needed for image processing, model building, evaluation metrics, and visualization. Now, this part is responsible for This part is responsible for loading the data set, generating the data frames of image file paths with their labels, building the model, training it, and evaluating it. Especially this first cell runs the entire pipeline from data preparation to model evaluation. Now we downloaded the X-ray dataset directly from Kaggle using Kaggle Hub, so anyone running this code in the future can reproduce the same results without manually downloading the files. And we list the file paths, assign the labels as normal and pneumonia, and split the dataset into training, validation, and testing. If validation is insufficient, it automatically splits up training data. The model begins by loading the dataset, applying pre-processing, and then training the ResNet50 classifier in two stages. First, the classification head, and then the fine-tuning backbone. After training, the system evaluates the model on the test set and prints the performance metrics. Here, the output shows the classification report, which summarizes how well the model performed on each class. The output shows the classification report. Our model achieves around 92% accuracy and ROC AOC of around 0.9, meaning that model has very strong discriminative capability between pneumonia and normal cases. And here the graph visualize the model training progress. They show how the training and validation accuracy or loss changed over each epoch. Here we can see the epoch train. And a stable high accuracy and decreasing loss indicates the model is learning well and not overfitting. Now, this is the confusion matrix. Here we have it visualizes the model predictions. It helps in visualizing the model predictions. And let's move on to the second cell. This part of the code performs interference of the single X-ray image. It loads the image, pre-processes it, sends it to the trained model, and then displays the output classification. And additionally, it generates GradCam visualization. Let me show you that. This is the part that involves GradCam, and it helps with it helps in highlighting the specific lung regions that influence the model decision. So let me run this. Here the output appears. So we have to select the image. So let's take a normal image, for example. Any image we can take from the data set. Here the model predicted this scan is normal, and if we look at the GradCam map, we can see very limited or no red activation. This means the model did not detect abnormal patterns or infection capacity. We can see it clearly here. Now let's take another file which has pneumonia. So we can take any image from the data set. Now let's take a image here. Yeah, we got the output. Uh, this this shows the clear difference between the normal and the pneumonia. The model predicted this image as pneumonia with high confidence. Here, 99% probability that this person has pneumonia. And here the GradCam visualization highlights the infected lung regions shown in the reddish areas. This demonstrates that the model is making medically relevant decisions rather than random guessing. Now, yeah, we got the two cases. We have seen the two cases here. Thankfully, we did it in the two cells. We completed one cell with training the data and everything, and the second cell with testing the data. Like we have taken the data from Kaggle, and yeah, and this concludes our project, and that the conclusion of the project, the demonstration of our pneumonia detection system using ResNet50. Our approach provides high performance and visual interpretability for cleaning confidence. Thank you so much for watching the entire video, and I hope you understand the project. If you have any questions or comments, we are here and we'll be happy to answer them. And this is our final output, and our project is pneumonia.